Hello everyone, in this video we are going to see a numerical on design of single angle strut. See, the numerical is, the statement is like this: design a single angle discontinuous strut to carry a factored load of 65 kilonewton. Assume distance between its points is 2.5 meter. Use Fy is equal to 250 MPa, that is megapascal. Both ends are hinged, that you have to assume. So this much data is given to you. Let's calculate. First, what I will do, I'll not start answering this question. First I will write down the all the data or all the steps which will be required, so that you will easily understand this. First, what you have to do, you just write down the given data, whatever it is given. Then the next step you should follow is calculate the effective length. What you should do next, you should calculate the effective length. Then the third step is corresponding FCD. Now I will tell you what is corresponding FCD. For that, see, you have to assume certain value. What assumption you have to make, I'll tell you. See, you have to assume the value of lambda. Lambda is nothing but slenderness ratio. As it is not given in the numerical, you have to assume certain value of lambda, that is slenderness ratio, and from that you will easily calculate the value of FCD. So the first step that you should do is assume certain value of lambda, that is slenderness ratio. So what will be the value? So what I will do, I will give you one table here, and from that you can refer this table and you can assume the value of lambda or the slenderness ratio. So you can write down this type of table in your book also. I'll write type of section on one side, and on other side I'll write lambda. Okay, so the first type of section is single angle. If the type of section is single angle, then assume the value of lambda in between 100 to 150. That's it. Then if the type of section is double angle, if it is double angle section, what should be the value of lambda that you should assume? It should be in between 80 to 120. Now you will get confused that why I should assume the value of lambda. I'll tell you, because you have to find out the value of FCD. This FCD is nothing but the stress. Corresponding FCD is nothing but your the stress. So this stress has to be calculated. That this is known as, see, full form of FCD is design compressive stress. FCD is what? Design compressive stress, and this should be first assumed, then later it is calculated. But first, as the section is not given, how you will decide that what section you should use? Because see, they have given just single angle discontinuous strut, they have not given any section. So for assumption of section, you must know from value of lambda you will calculate certain value of FCD, and from FCD you will calculate you will try certain section. Okay, so that is what I am trying to explain you, and you will understand it. One, just write down the steps that you have to follow, and ultimately I'll explain this total full numerical to you. Then the third step, the third type of section will be single channel. If you are using single channel section, then what should be the value of lambda you should assume? You should assume the value of lambda in between 90 to 150. Then we have fourth type of section, that is double channel. If you are using double channel section, then what should be the value of lambda? So the value of lambda should be in between 40 to 80 for double channel. Remember this. Then only two sections you have to remember. Single eye section. For single eye section, the value of lambda must be in between 80 to 150. And the last one, double eye section. So for double eye section, the value must be or should be taken in between the 30 to 60. So these are the steps that you have to follow. Okay, I'll explain one more steps. So once you got the value of lambda, immediately calculate the value of FCD, and this FCD value will be taken from the IS code. I'll mention the page number here. Actually there are so many tables, I'll not mention here. I'll mention that in while calculating or while solving the numerical, I'll not mention here only, because there are 2 to 3 pages on which FCD is given. So it is a range of page numbers. That's why I'm not mentioning it. Just remember it is given in IS 800 2007. Okay. Now the next step. What next step you should follow? Once you got the value of FCD, you should calculate the area required. What will be the area that you should assume for a particular angle section? So area required will be taken. How area will require will be calculated? It is taken from the simple formula of stress is equal to force upon area. This formula you may be knowing from very first year. So how you can calculate the area? It will be force divided by stress. So force will be given in the numerical. Here it is 65 kilonewton. Here it is, and stress we have calculated, that is nothing but your FCD. This is your stress, design compressive stress. So once you get force, it is given, FCD you have calculated, easily you will get certain area. Certain area will be so and so mm². You can convert it into the centimeter square, and next step will be you try the section, and obviously you should try that section which is greater than the area required. So next step will be the try section, and section try will be from which? It will be from steel table. You have to refer steel table for trying certain section, and it should be greater than the area which is required in the step with that you have calculated. Now comes the important steps. See, now you have to find out 2 to 3 things. I'll write down here. You have to find out first lambda E. It is given in IS code. This formula is given in IS code, so you don't need to worry. Lambda E, I'll mention the formula later. Just write down the steps. Then you have to find out lambda VV, then lambda phi, and ninth step only phi. Lambda phi and phi. Actually, lambda E has a big formula, and it depends upon these values. What? Lambda VV and lambda phi. So before calculating lambda E, you should calculate lambda VV or lambda phi. So you can take these steps above that directly, or you can write down in these steps in this manner only. Then the 10th step. You have calculated all the required steps. Now what is the 10th step you should follow? Finally, you will get design compressive strength. I'll write down only in simple words, design FCD. Okay, and design FCD, once it is calculated, the last step is to calculate design compressive strength. Design compressive strength of compression member, and in our case compression member is which one? It is strut member. And remember, design compressive strength, that is PD, I'll denote it by PD. It is area into FCD which you have calculated in step number 10. Okay, area it is here which you have tried from the steel table. Here you will write down the properties, and FCD you have calculated in the step number 10, and it should be greater than, obviously your design load should be greater than the given load. For example, this load is 65, so obviously your design load must be greater than this. There, then and then only your section will be safe, otherwise it will be unsafe. So these are the steps that you have to follow. So what we will do, you just write down all these steps on a paper, and then we will start solving this numerical, so that in one numerical only you will understand all the concepts related to the design of single angle discontinuous strut. So just write down, you can pause the video and you can write down all the steps which will be required for going up to the final step, or for calculating the design compressive strength. So let's start with the numerical now. I have given you all the steps. Now let's start solving the numerical one by one. So the first step, you have written that steps on the paper. I'm assuming that you have written those steps. So I'll write down the first step only, that is given a data. What is given? That I'll write here. So what is given? PU they have given, ultimate load. It is 65 kilonewton, ultimate load or factored load. You can even convert it into the Newton, but I think there will not be any need for conversion. So just write down whatever they have given. Then Fy they have given. It is how much? 250 Newton per mm square. Then they have given that both ends are hinged. They have mentioned that. Okay. Then the next step, length they have given, it is how much? 12.5 meter, and they have mentioned that the type of structure is, or type of member is, single angle discontinuous strut. So I'll just write down single angle strut. So these are the steps that they have given. Now let's find out the next step, that is effective length. I have given you the steps. Effective length. So what is the formula for effective length? That I will show you. See, the effective length is given generally by LE or K into L. So K value will be 1 because both ends are hinged, and it is L value is 2.5, so it will be 2.5 meter only. Now where I got this value? I got this value from page number 45 of what? Of IS 800 2007. You can check that page number. They have given all the effective lengths. Actually, we have seen this concept. I have also shown you the screenshot from this IS code. That's why I'm not showing you it here again. Just open the IS code. And one more thing, why I'm not showing you the IS code? Because you will open this IS code by yourself, so it will be practiced. You will be habitual of using the IS code because you have to use the IS code so many times. So from page number, just go to page number 45. There is a table given there, and from that table find out if both ends are hinged, what will be the value of K. So they have given the value of K is 1L. So just put 1L. 1L means 1 times 2.5, that is 2.5 meter. Okay. Now the third step. Third step is what? You have to calculate the corresponding FCD. So I'll write here third step. Now to find out the value of corresponding FCD, I have told you that you must assume certain value of lambda, that is slenderness ratio. So just go back to the previous step. See, I have given you this table. For single angle, what is the value of lambda? It should be in between 100 to 150. So in between 100 to 150, I can assume anything, any value. Okay. So I'll assume the value of lambda as 120. What I'll do, I'll assume the value of 120 lambda value. Now what I will do, see, now I will show you a page from IS code. Why this value is needed, I'll show you that. So this is the page from IS code. I have opened the page number 42 from IS code, and there is a table here. We have to find out the value of FCD. What was the assumed value? What was the assumed value of lambda? Lambda is nothing but KL by R. Here it is. So for that we have assumed this value. Okay, that is 120. Here it is. So 120, for 120 you have to find out what is the value of FCD. See, the table says design compressive stress FCD for buckling class C. One more thing, for buckling class, for every angle section the buckling class will be C only. For every angle section buckling class will be C only. Yeah, that you have to remember. Even in IS code they have given this. Okay, so I am not just randomly saying you this. For every angle section, just remember the buckling class will always be C, because there are various tables. Even for buckling class B also they have given one table, but you will not refer this table. Even for buckling class A they have given table, but you will not refer this table also. So which table you will refer? Buckling class C table will be referred if the type of section is angle section. So angle section I am using buckling class C. I have assumed a value of 120. So for 120, what is the value of FCD? See, our Fy yield stress is 250. So for 250 value, let me show you this. See, for 250 value, the value is 83.7. What is the value of FCD? It is 83.7. Here it is. I'll zoom it. Wait a minute. For 120, the value is 83.7. Here it is. This value I'm talking about. And why I'm referring this 250 column? Because our yield stress Fy is 250. We always take 250. Okay. So that column is exactly matching with 83.7 Newton per mm square. Okay. So this value you have to take. Now I will go back to the numerical. That is our question. Okay. So So I have shown you the table. So which was the table? I will mention the page number also here. So the page number was 42. What was the table number? Table number was 9C, and from that we have taken the value of FCD as 83.7 Newton per mm square. Okay, for Fy value of 250. So once we got the value of FCD, let's calculate the area required. What I will do, I will find out what is the area required for this FCD. So I'll write down that step. Next step, you can check. I have told you to write, or you can just rewind the video and you can check what are the steps that I have given you. So required area. For required area, the formula, I have told you formula also. It is what? It is area. See, I'll write like this. Stress is equal to force divided by area. So if you want to calculate the area, area will be equal to force divided by stress. Now, what is the value of stress and what is the value of force? Force is 65 kilonewton, but in Newton it will be 65 into 10 raised to 3, and divided by stress. What is the value of stress? We have assumed this 83.7. So for that, the area required is 776.58 mm square, or in centimeter square it will be 7.76 centimeter square. Now what you should do, you open the steel table and you find out that section which has area greater than this. So I will assume one section. That is my next step. So I'll put step number 5th as try section. I have to try certain section. Why I'm using word try? Because I don't know whether it will be safe against this 65 kilonewton or not. So I'm just writing try. So from steel table, you can open the steel table, you can refer that. From steel table, I'm using this section. Try ISA 75 by 75 by 6 mm. This section I am trying. So its area is how much? Let me tell you. Its area is 866 mm square, or in centimeter square it will be written like this, but we don't want it in centimeter. That's why I have written this area 866 mm square. And one more property you need, RVV. It is 14.6. You can open the steel table and you can find this section 75, 75, 6. And for that, what is the area? You check it. And what is the value of RVV? You check it. Now, we have calculated, we have tried certain section. Now, let's calculate one by one. What are the next steps that I have given you? So, the next step I have told you is the equivalent slenderness ratio. That is the 6th step. Equivalent slenderness ratio. In short, it is written as lambda E, like this. Lambda E is equal to under root of K1 plus K2 into lambda VV square plus K3 into lambda phi square. And I'll tell you, this is given in IS code. I'm telling you again and again. This formula is given in the IS code. Let me show you this formula in the IS code. See, here it is given in IS code. Lambda E is equal to under root of K1 plus K2 lambda VV square plus K3 lambda phi square. Now, I'll tell you one thing. You have to find out the value of K1, K2 and K3. Because you don't know the value of K1, K2 and K3. Even lambda VV and lambda phi are not known. But lambda VV, they have given you the formula. Here it is, lambda VV, and lambda phi, it is also given here. But what about K1, K2 and K3? They have given it in the table number 12. Which IS code I am using? I am telling you again and again. IS 800 2007 I am using, and this formula is given on which page number? It is given on page number 48. You can write that. From page number 48, I have taken this step, that formula. Okay. Now talking about K1, K2 and K3. Let's come back to this. So it is given in this table. it is given in table number 12, K1, K2 and K3. It is saying if number of bolt is only 1 and the support is fixed support or hinge support, then they have various formulas for K1. Let us assume, I'll tell you one thing. See, if I'm telling you that the number of bolts are 2, what I'm saying, the number of bolts are 2, okay. So for 2 number of bolts and they have given both ends are hinged, that is also clear. So 2 number of bolts and hinge support, what is the value of K1? It is 0.70. What is the value of K2? It is 0.60. And what is the value of K3? It is 5. So you will get the value of K1, K2 and K3. So it is how much? It is for 2 number of bolts, I am assuming 2 number of bolts. For that, for hinge support the value of K1 is 0.70, K2 value is 0.60 and K3 value is 5. Now I can put these values K1, K2 and K3 here. Now what about lambda VV square and lambda phi square? So lambda VV, they have given this formula. It is L by RVV epsilon under root of pi square E divided by 250. Okay. And lambda phi is B1 plus B2 divided by 2t whole divided by epsilon under root of pi square E divided by 250. Now you can put the values and you can find out the lambda VV and lambda phi. Now you just pause the video here and you note down all these things. See, epsilon they have given yield stress ratio and it is given by 250 divided by Fy raised to 0.5. So 250, what is the value of Fy? It is also 250. So 250 by 250 will be 1 and 1 raised to 0.5 will be 1. So that value will be 1 only. Then, so I can calculate that epsilon also. T is the thickness of leg. That is easy. B1 and B2 are the width of two legs. We have used 75, 75. So B1 and B2 will be 75, 75. Okay. So in this way you can put these values and finally you can calculate the lambda E value. Okay. So I have shown you what is the value of K1, K2, K3. You just write it. I am assuming 2 number of bolts. Type of joint is hinged only. So for that the value of K1 is 0.7, value of K2 is 0.6 and value of K3 is 5. Just write down this. Pause the video and just write down all these values K1, K2 and K3. Now coming back to our numerical. So from where I got this value? I got this value for this formula from page number 48 of IS code. Now what I will write? I am assuming 2 bolts at each end. At each end I am assuming 2 bolts and end condition is which one? End condition, I'll write here, end condition is hinged. Which condition is given? Hinged condition. And remember, in exam you have only this type of condition, hinged condition only. See, they have given both ends are hinged only. So you can easily find out that. Now, so I will be using from table number 12. Which table I used? I have shown you that in the IS code. From table number 12, page number 48, what is the value of K1? I told you to write it on your paper. It is 0.70. What is the value of K2? It is 0.60. And what is the value of K3? It is 5. I have told you this. You have to write the values of K1, K2 and K3. And from where I got this value? I got this value from page number 48 of IS 800 2007. Now, I got all the values from table number 12, page number 48. Let's calculate rest of the things. See, K1, K2 and K3 are known. Let's calculate lambda VV and lambda phi. So I'll put lambda VV is equal to, it is L by R VV whole divided by epsilon under root of pi square E divided by 250. In IS code they have made one mistake. It is E. It is not epsilon. Okay. So you may make that correction. Now what is L? L is given. It is 2500 divided by RVV. We have taken this from the steel table. It is 14.6 whole divided by epsilon. I have told you what is the formula for epsilon. They have given in the IS code. Epsilon is equal to 250 divided by Fy raised to zero point 0.5. They have given this formula. So 250 divided by Fy is also 250 raised to 0 0.5. It will be nothing but 1. So I'll put 1 into under root as it is, pi square as it is, E. What is the value of E? Modulus of elasticity of steel is 2 into 10 raised to 5. You have to remember this. Divided by 250. So the value of lambda Vv after the calculations will be 1.927. You can pause the video and you can do the calculations by yourself. It should come 1.927. Okay. Now we got the value of lambda Vv also. Let's calculate the value of lambda phi. Only lambda phi value is remaining. Rest of the things. Then finally I can calculate lambda E. Okay. So I'll find out lambda phi. So what is the value of lambda phi then? I'll put here lambda phi is equal to b1 plus b2 divided by 2t whole divided by epsilon, and it is given under root pi square e divided by 250. Okay, so what is the value of b1 and b2 then? We have used which section? Let's go back to the step. Which section we have used? We have used this section 75, 75, 6. Okay, so I'll put 75 plus 75. 75 plus 75 divided by 2 into thickness. Thickness is how much? It is 6 mm. And whole divided by epsilon. Epsilon is 1. We have calculated that just in the last slide. Divided by pi square into 2 into 10 raised to 5. It is E. Okay. In IS code they have mistakenly mentioned epsilon. Divided by 250. So what will be the value of lambda phi then? It is 0.1406. Now we got all the values. You can easily put these values and you can find out this lambda E, K1, K2, lambda VV and so on. Okay, so I'll put that values and I'll find out the value of lambda E. So therefore I'll write lambda E is equal to, I'll again put the formula here for your better understanding, K1 plus K2 into lambda VV square plus K3 into lambda phi square. Okay, now what was the value that we have calculated for K1? We have taken it from table. K1 is 0.70. So I'll put 0.70. What was the value of K2? It was 0.60. What was the value of lambda VV? We have calculated it as 1.927 square. What was the value of K3? It was 5. And what was the value of lambda phi? Here it is. It is 0.1406 square. So the value of lambda E will be 1.739. This is the value of lambda E. Now the next step is the calculation. Next step is how much? It is sixth step. No, then the seventh step. I'll put seventh step. Actually we have changed certain steps. See, in giving the steps I have told you that you should separately calculate, you should take separate steps for lambda VV, lambda phi, but what I have included, I have included this lambda VV and lambda phi in this step only, in sixth step only. So my phi step will be the seventh one. Okay, so coming back to our steps, so my seventh step will be phi. So what is phi? Phi is equal to 0.5 in a bracket. It is again given on same page numbers. Okay, 48 page number. You can find out that formula. Lambda E minus 0.2 plus lambda E whole square. So this is the formula for phi. Now the question is, what is the value of alpha? Because rest of the things you know, lambda E is known, 0.2 is just number, 0.5 is just number. What is the value of alpha? So alpha is taken from table number 10. Just open the IS code and from that table number 10, which is given on page number 44. You open just that page number. See, I told you what is the buckling class. Buckling class is what? Buckling class is C, always. For what? For angle sections. So if buckling class is C, they have given in on page number 44, table number 10, value of alpha, and it is given as 0.49. Okay, so you have to put this value 0.49 in this. So my alpha value will be 0.5 in a bracket 1 plus 0.49 in a bracket lambda e, it is calculated here, 1.739 minus 0.2 bracket close plus again 1.739 square. So after the calculations, the value of phi is 2.389. If you still get confused what is the value of alpha, let me show you the IS code. From that, how I got this value of alpha as 0.49. See, this is the IS code. I have told you which page number. It is given on page number 44. So you just open the page number 44 in IS code. Here it is, page number 44. What is the type of section? Channel section. Sorry, angle section we have used. For angle section, what is the buckling class? Here it is, the buckling class. See, on top it is given buckling class. So buckling class for channel section is C. So for C class, what is the value of alpha? Let's see. I'll show you the value of alpha. They have given here. Wait a minute. See, this is the value of alpha. Table number 7. Value of alpha. Buckling class is C. So for buckling class C, value of alpha is how much? 0.49. So on which page number they have given? 35. So you have to refer actually 2 pages. I just mentioned 44. I will also mention page number 35. So on page number 35, value of alpha is 0.49 and it is table number 7. So coming back to our numerical, yes. So I'll mention here that this alpha is taken from page number what? Page number 35, table 7. Okay, it was table 7, page number 35. Alpha value was 0.49. So my phi value was 2.389. Now I have calculated the value of phi. So why we have calculated the value of phi? Why we have done so many procedures? Because ultimately we wanted this phi value, and for phi value we wanted lambda e value. That's why we have calculated lambda e value, and for lambda e value we wanted lambda vb and lambda phi. That's why we have calculated these values. So it are all these are interconnected. Now the next step is step number 8. So I'll put step number 8 here. I'll write step number 8 here, which is nothing but design compressive stress. You can check the steps. Design compressive stress. It is given in, I'll mention the IS code clause number. It is given in clause number, CL means clause, okay, clause number 7.1.2.1. I'll also mention the page number 34 of IS what? IS 800 2007, so that it will be easy to understand. So what is the formula for FCD? It is given like this. FCD is equal to Fy divided by gamma m0 whole divided by phi plus again phi, but this time square, minus lambda e square raised to 0.5, and it should be greater, less than or equal to Fy by gamma m0. Okay, now I'll put all these values. Fy is 250 divided by lambda m0, that is 1.10, whole divided by 2.389. This we have calculated just in the previous step. In a bracket again 2.389, but this time square, minus lambda e, that is 1.739 square, bracket close, raised to 0.5, and it should be less than or equal to 250 by 1.10, because Fy is 250 and gamma m0 is 1.10. So after the calculations, it comes as 56.435, and it is obviously less than 227.27 Newton per mm square. Okay, this one is also in Newton per mm square. So FCD value is calculated now. Now only the last step remaining, but there are chances that your section will fail. Okay, so again you will have to do the same procedure. So my 9th step will be design compressive strength. That is my last step, design compressive strength. But there are chances that your section will fail. Okay, there is possibility actually. PD is equal to area into FCD. In IS code they have given AE, that is nothing but the area. Okay, so what area you have assumed, let me go back to that step. What is the area that we have taken? We have to take this area, trisection. It is 866 mm square, so I will be using that area only, 866. And FCD value we have calculated just in the previous step, it is 56.435. So I'll put 56.435. So after the calculations, it will be 48.87 kilonewton. Now the problem is it is less than PU. So it is not safe. That's why I'll write it here. The section ISA 75 by 75 by 6 mm is unsafe. It cannot resist PU, because PU was what? It was 65 kilonewton and our design compressive strength is only 48, so it is not safe. It cannot resist. So what is the next step then? You have to repeat all the steps from this from where I'll tell you, from this only. See, required area was 7.76 and we tried the area of 8.66, so it is not very useful. So what you will have to do, you will have to increase the size of section. Now this time assume some different sections. So that's why I have given you the heading of this video as single angle strut part 1. This is only part 1 because I knew that this section will fail. So in next video what we will do, we will try this section, try another section. You can write like this, try another section, and I'll try this section, try ISA 90 by 90 by 8, and whose area is how much? It is 13.79. You can check the steel table, and in mm square it will be 1379 mm square, and its RVV is given, it is 17.5 mm. Now from this trisection, which was that step? It was step number 5th. So from step number 5th, this one is over. Now from step number 6 you have to repeat all this procedure from step number 6 to step number 8. You just repeat step number up to step number 9. You repeat all this procedure and you will check whether this section is now safe or not. So in next video I will show that procedure will be same. You can even try it by yourself, and if you face any difficulty you can watch that next video, that is part 2. Okay, thank you.